Hello guys, in this video I would like to explain that how you can perform regression analysis in Python, and particularly we will focus on simple linear regression analysis. I hope you know that what is meant by simple linear regression analysis. A simple linear regression analysis is the regression in which we have only one dependent variable and one independent variable. I have talked about this in the previous video where there were 5 steps we have talked. So the link to that video is mentioned in the description of this video. You can visit that video and know about basics of simple linear regression. You need to understand the basics, otherwise you will be unable to interpret your results. Okay, so this is all about simple linear regression analysis. Now, how we can do this in Python? I have done a video in that how we can do simple linear regression analysis in R, and the link is given in the description of this video if you want to see how we can do in R. And today we will do this simple linear regression analysis in Python. So let's move to Spider, and you need to these libraries. You need to import pandas SPD and state model .api as sm. You can go and you can see the detail, because this we are using for regression analysis. You can see that the model as sm. So from here and .ols, and then the model. So let's import each of them. And you can see here there is no errors. This means that successfully imported. Okay, then SNS and then NumPy. Okay, we have done these. Then you need to do this because you need to enable line plotting for the Jupyter notebook. This can use here as well, but this is just mentioned here. Okay, now I need to load the data from online. In this case, I'm using online data, but you can use your own data, as I have done a video that how we can import data from CSV file in Python. So you can use that way and you can read your data, and then you can work with your own data as well. And after this example, we will have an regression analysis with the simulated data. So that will explain everything to you. You can work with your own data by importing the data. You can work with the online data, and you can work with the simulated data just for explaining our learning purpose. Of course, you will work with your own data when you are working in the real, or you are dealing with the real world problems. Okay, so this data is empty cores, and I explained this in the previous video. Again, you need to visit that video for this description as well. So just this URL is from this until empty cores.csv. So this data is stored in this one. You can read directly as well. pd.read.csv and just mention all this stuff. So you will see. But anyway, this is the two-step procedure, 1 and 2. So now you have read the data. The data is stored in the empty cores now. And this is just to identify X as an independent variable and Y as dependent variable. So this is horsepower and this is mile per gallon. This is again explained in the previous video, in which I explained simple linear regression analysis in R. So this is now X, now independent variable, and this is the dependent variable. And if you want to include constant or intercept, you can just using this command. This will include constant your model, and now you need to estimate the model. With every step there is something written, so you can read that. Load the data, enable inline plotting for Jupyter notebook, define the predictor and response variable, add a constant term to the predictor, fit the regression model. So this model will fit the regression model, and that is model. I just mentioned model 1 here because I have another data, and that is model 2 part to make a clear difference between the two. So now fit the regression model using this command as a sim.ols y comma x dot fit. So using this, yes, there is no error, so it's properly working. But remember, you need these libraries, particularly if for this command, this one, import states models dot API as is. And now print the summary of the model. This is very important command in Python in regression modeling particularly. You need to understand this as well. I'll just run this command and I have a lot of statistics. Yeah, this is very beautifully printed and the table is created in Python. You can see dependent variable mpg because if you know mpg is a dependent variable, then of course horsepower is the independent variable. It is not mentioned by the way here. Model is OLS, the method of OLS, and you can see the important thing, number of observation, residuals, because there is 2 parameter. Okay, and okay, coherence. Okay, the important thing which you need is R square. We will explain this sometime later. This is very important for to see how the model worked, how better the model worked, because this explains the variation in the observed data. So this means that 60% of the variation explained by this model in the observed data, the response variable. So still it is low, but in some problem it is okay. It's dependent on the problem. Adjusted R square, you can see in this F statistic, probability of F statistic, so p value, and log likelihood, and AIC, BIC. These 3 criteria you can use for model selection. Remember, log likelihood, AIC, BIC, and also R square and adjusted R square. So you can use these for model selection. If you have 2, 3 model, 4 model, or more than 2 model, more than 1 model, you can use these statistic, and you can go and see the definition of these statistic. Then you can decide which value is better, lower or higher. So I will explain this sometime in another video, model selection criteria. And the method here is used as least square, of course, it's mentioned here clearly. Okay, this was something for model selection and other statistics. Now this is now the parameter, the coefficient. This is constant 5.5484. So this is constant, and the coefficient which we normally say alpha in the regression equation, and this is HP. This is the coefficient of independent variable, that is minus 0.0076. So this is the change in the response variable, the mile per gallon, by changing per unit change in the horsepower. I will explain this sometime. I just need to write and just Google simple linear regression formula. Okay, I'll explain here now easily. So look at this equation. The y is mile per gallon. This is constant. Beta naught, which we have 5 point something. Like this is beta naught 5.5484. And beta 1, this is beta 1 as this value minus 0.0076, and this xi is horsepower. So this equation you can write mile per gallon equal to 5.5 something plus minus 0.0, you can write not plus minus 0.007 horsepower. So this will be your model according to that. If you replace with the y and x and define that y represent mile per gallon and x represent horsepower, then of course you can write like this. So this is the interpretation. This value represents the rate of change in the response variable as per unit change in this variable. So you can explain this parameter. Now I will explain this, but I need to write. Then I will explain, not like this. And this is the p-value for this constant. The beta naught you can say from the regression, from the in which I explain from here, beta naught, and this is beta 1. So, and this is the p-value for beta 1. So both are highly significant. Both are highly significant. And this is 95% confidence interval for the constant or the beta naught for this value. And this is the 95% confidence interval for this value, I mean the beta 1. So you can see a lot of information in this table, but you should know how to interpret these values. And now this is also a test. You can see this in detail, and then you can see what is meant by this, and the p-value is mentioned, so you can explain. This is skewness kurtosis. You can see skewness is close to 0 and kurtosis is close to 3. So in the case when the skewness is close to 0 and kurtosis is close to 3, this means that the distribution is close to normal distribution, not exactly normal distribution, but it's look like close. But we need to draw histogram and QQ plot, so then we can see to confirm. And these are the two tests, Durbin-Watson test and Jog-Bira test. And this is the probability for Jog-Bira test, the p-value. So you can see that the p-value is higher. So this means that we reject the null hypothesis, but we don't know what is the null hypothesis. For that, we need to see to Google it. And Durbin-Watson test, this has some range. So let's see Durbin-Watson test and then Jog-Bira test. And then we conclude because we don't know about the null hypothesis. And in the Durbin-Watson test, we need this has some range. Okay. Okay. So this is something like, you can see this is not full. You can see from somewhere. Do not reject. No evidence of autocorrelation. So this gives you something about the autocorrelation. We need to see. Let's see here. Durbin-Watson statistic is a test for autocorrelation in the residual from a statistical model or regression analysis. The Durbin-Watson statistic will always have a value ranging between 0 and 4. A value of 2 indicate there is no autocorrelation detected in the sample data. So you know that if it is close to 2 or it is 2, not close to 2, because you need to go and see the detail. Just Google it and see the detail, and then you can decide about the null hypothesis in this case. Otherwise, you cannot decide about this. So in this case, it is less than, of course, less than 1.075. So this means that there is autocorrelation. You can interpret this when you read about the Durbin-Watson test. Now let's see what is the null hypothesis in Jog-Bira test, because of course we reject the null hypothesis. The p-value is, this is 0.64. We reject the null hypothesis, but we don't know. So two things are important, the p-value and the null hypothesis. Null hypothesis, Jog-Bira test. The null hypothesis, giant hypothesis of the skewness being 0 and the exceed kurtosis being 0. So this means that the null hypothesis, samples from a normal distribution have been expected skewness 0 and expected excess kurtosis of 0, which is okay. So this means that they simply say that if the skewness is 0 and the kurtosis is the skewness is 0 and the kurtosis is exceeding being 0, this means that okay, Sample from normal distribution have an expected skewness of 0 and expected x is quartus of 0, which is the same as the quartus is 3. So this means that the data is from normal distribution. As earlier I explained that for normal distribution, normal data, the skewness is 0 and the quartus is 3. So this is the same thing in different way. So this means that the data is normally distributed. This can be the alternate, in the other word, hypothesis. So you can see that the p-value is 0.640. This means that the skewness is not close equal to 0 and the quartus is not equal to 3. So in other words, the data is not normally distributed. So these are the two tests which you can use. You can see about the autocorrelation and the normality of the residuals. However, you can use Anderson-Darling test, Shapiro-Wilk test, and other tests for normality. I explain Shapiro-Wilk and Anderson-Darling test in my previous video. The description is given in the the link to that video is given in the description of this video, but that is explained, and or you can see and you can do that in Python by yourself. So this is all about the model parameter, the coefficient, the test, normality, etc. Now we can plot the data and see how it look like, because this was everything here was numerical. Now we can plot. So this is the plot size. Yes. Here, okay. Okay. This will give you just the regression line, and the data in the regression line you will see. So this is the regression line and the data point in the regression line, horsepower independent variable or miles per gallon independent variable. You can see the slope is of course minus. This is the slope is negative, decreasing. And now you can see calculate the residuals. So I will just assign residual 1 because I have another model. For that I have residual 2, 1, and everywhere I need to place 1. So model 1. Now I need to plot QQ plot and see how it look like. Okay. Yeah, the extreme values are far away here also, and here these values can create problem. So let's see how we can now we can see the histogram by using these set of commands and see how it look like. Okay, so you can zoom out this. Okay, you can see it is not normally distributed. Yes, like this. It's close, but of course it is not like that. Okay, because the values are here, and these are the extreme values about which I talk in the QQ plot. So this is all about regression analysis, simple linear regression analysis in Python. So if your data is not normally distributed, you need to apply some transformation to make it normal, like log transformation, inverse transformation, square root transformation, or Box-Cox transformation to make your data normal, because normality is one of the assumptions of regression analysis. If your model violate your assumptions and you do prediction, there may be problem in your prediction. Okay, the same thing I explained with now the different data. What just the data is that is generated from normal distribution to data set, independent variable x, dependent variable y, from normal distribution with in 5 for the x, standard deviation 3 and 100 observation, and similarly 50 mean, 5 standard deviation and 100 for y. Just do the same thing. Now we have already variable, and do the same thing and add constant value to this variable. Model 2 now, because that was model 1. Okay, and now print summary to see how it look like. Yes, this is now different because the coefficient are quite different. In there that was 5 point something, and this was minus 0.00 something. So this you can see the coefficient is different. This is different. The p-values, the p-value for here constant is significant, but this is not significant actually. The beta one, and this you can see these values curves. You can see these values skewness and kurtosis. Yes, here it's close, but we're not sure about this whether it is normally distributed or not. Durban Watson is 2, which is close to 2, by the way, and Jogbira is 3, and the probability that we will have Jogbira is 0.2. So it's still not normally distributed. However, now let's see residual 2, model 2. Okay. You can see this is the plot now with this data. So yeah, there's some values are here outside, some here outside. The extreme values lower and upper extremes outside the line. Let's see. Now again, the same way I can plot residual 2, remember not residual 1. Model 2. Yeah, it's not normally distributed, by the way. It is skewed to this side. No, negatively skewed. So of course, the data support, numerical data support, the graphical result is not normally distributed. And we check numerically as well as graphically, so we confirm that the data is not normally distributed. I will try in the next video to make the data normal, the non-normal data normal in the next video, so you can see how we can do this stuff, because this is important and your model should satisfy the assumptions. So this is all about regression analysis in Python, simple linear regression analysis in Python. And if you have any question, please write in the comments so that I can address whatever you want to know to learn more. And thank you very much, and see you in the next video.